Okay, so in this system we've got 100 kilograms an hour of crushed sugar stalk coming into the extraction process. So first thing to do is probably to label the different components in the system. So water is our solvent, so that's going to be C. Sugar is what we're trying to extract, so that's going to be component A. And then the pulp is the inert solid, so that's going to be component B. And the composition of the sugar stalk coming in is given in the question. So water is going to be a C, so that's going to be 38 kilograms. B is going to be our pulp, so that's going to be 52 kilograms, and then A is our our sugar, so that's going to be 10 kilograms. And we know that 95% of the sugar is going to be recovered, so in the extract stream up here, we're going to have 9.5 kilograms of sugar. And since it's an overflow stream, we're going to have no solids, so B is going to be 0 up here. And we don't quite know what the amount of solvent is just yet. So this is our first stage here. It's going to be a multi-stage process. So we're going to have a few more stages later on. We'll just label those as n-1. Okay, so let's look at what's coming out of the other end. So doing a balance on A, we can say that there's going to be 0.5 kilograms coming out down here. The reason for that is we're using, I think it says in the question, impurity-free water as the solvent. So in other words, there's no A up here. So that's going to be 0, and that's just a simple mass balance on component A. And same thing, since it's a pure solvent, there's going to be no solid up here either. What else do we know? We know that B is going to be 52 kilograms down here because the solid stays in the underflow streams. And what do we also know? We're also given that each kilogram of dry pulp retains 2.5 kilograms of water. So in our system we've got 52 kilograms of dry pulp. So therefore that's going to retain 2.5 times that of water. So what we can say down here, C is our water. C is going to be equal to 2.5 times 52. That's going to give us 130 kilograms of water. Okay, and we're also given that the concentration of the extract phase leaving the system up here is going to be 12% sugar. So that means that we can figure out how much water we've got in that stream up here. So we know that Y1, the concentration of this phase up here, is going to be equal to the mass of sugar, which is 9.5, divided by the total mass of solution in that stream. So that's going to be equal to V1, we'll just label it that for now. And then in the question that's given to be 0.12. So simply by rearranging, we can calculate that V1 is going to be equal to 79.17 kilograms. And then from that we can easily figure out how much C is in that stream. So that's going to be 79.17 minus 9.5. It's going to be equal to 69.67. So we're almost finished with our material balances. The last thing to do is just to figure out the amount of solvent we've got coming in. And then that's pretty simple. That's just simply a case of going in minus out. So we've got, coming out, we've got 69.67 plus 130 down here, and then minus 38 coming in. So that gives us 161.67 kilograms. So that's your mass balance done, and you need to do that regardless of which way you choose to solve the question. So regardless of if we're using the McCabe-Thiele method or if we're using the Punch-and-Savarit method. This is sort of the foundation for everything else we're going to do. So in the previous question, the previous example I worked through, I used the Punch-and-Savarit method. In this question, I'm going to use the McCabe-Thiele method. I think that one's probably a little bit more appropriate in this example, because when we do the Punch-and-Savarit method, remember we had the curve when we had n as a function of x, and that was given in a nice sort of tabulated fashion for us in the previous question. They haven't given us that relationship in this question, so for that reason I think it's probably easier to stick with McCabe-Thiele, and that will sort of be a different process. I think that's good to know as well. So, whoops. Okay, so we know, I guess first thing to figure out is this going to be a constant underflow process or a variable underflow process? And this question is actually, I wouldn't say misleading, but it's easy to get confused. The question says each kilogram of dry pulp retains 2.5 kilograms of water. And I guess it's quite easy just to read that and think, oh sweet, n is equal to 5, n is constant, therefore it's constant underflow. However, n is defined as, just write it out, mass of solution, sorry, mass of solid divided by mass of solution. And that's not actually what's given in the question. The question gives us the mass of water per mass of dry pulp, so it's not solution, it's given us water, and for that reason we can't say that n is going to be the same. In fact, n is going to change. So if we look at our process, we can see that this ratio to this ratio is going to be the same, right? B is going to be 52 all the way through, and then C is just going to be 2.5 times that. Unfortunately, A is not going to be the same, and because of that, this entire amount of solution is going to change, and that means that N is going to change. So this definitely isn't a constant underflow process. It's definitely going to be a variable underflow process. So we can still use the McCabe-Thiele method, but it is a little bit different. So if we did have a constant underflow process, remember for McCabe-Thiele we have our equilibrium line y equals x, we've got our operating line for the bulk of the stages, and then we have to analyze our first stage separately. And the reason we do that is because when we put our solid into our system for the first time, it's not in equilibrium with the other streams. So for that reason we have to plot that point separately, if you like. We can't just sort of extend our operating line a little bit further. Unfortunately, with variable underflow processes, this gets a little bit more tricky. And the reason for that is because the operating curve, the equation for that is L over Vx plus, I think it's V1 Y1 minus L0 X0 over V, I think it is. And the assumption in this case is that L over V is constant, and that's related to the fact that the N, or our underflow, is constant. So if you've got changing underflow, the slope's going to be changing, and hence this operating line is going to be curved. It's not going to be a straight line. But that's okay, we can work with that. What we do is I'll just get a different graph. What we do instead is we've still got our equilibrium line. We're going to calculate the start, the finish point, and we're also going to calculate the x and y values at what's called this intermediate operating point. And then just simply draw a line of best fit between them, and then just step off the stages as you normally would. So actually figuring out the x and y values for the start and finish is actually really, really simple. So I'll just go through that now. So let's think about what we've got up here. This is the start of our process, because this has got quite a high concentration of x, which is gradually going to decrease over time as we extract our solid. So this is going to be our sort of starting point, if you like. That's going to have the coordinates x0, y1. This point down here, this is going to be at the end of our process. This is going to have the coordinates xn, yn plus 1. And we've actually got all the information we need in order to calculate those values straight away. So let's go ahead and do that. So looking at our stream coming in. I should probably label these before we get going. This is L0, this is V1, this is Vn plus 1, and this is Ln. So we can see that those are just the 4 points, well the 2 points we need here. We've got all the data up here that we can solve those. So looking at L0, we want to figure out X0. That's simply going to be the concentration, well, the mass of A, which is 10, divided by the total mass of solution in the stream coming in. So that's going to be 10 plus 38. So X0 is equal to 10 over 10 plus 38. Remember, we're not fussed about the amount of solid that's in here. That's obviously not affecting our solution concentration, so it's just A and C we're worried about. So X0 we can calculate pretty simply. It's going to be, wait for it, it's going to be 0.2083. And then we also need to know the corresponding y coordinate, y1. So y1 is going to be the concentration of this phase up here, or this stream up here. So y signifies that it's going to be in the overflow stream, and then 1 indicates that it's coming from stage 1. So y1 corresponds to the stream up here. And again, it's pretty simple. y1 is simply going to be equal to 9.5 divided by the total mass of that stream, so 9.5 plus 69.67. And that's going to give us get my calculator out and do it instead, instead of searching around for the answer. It's going to be equal to 0.12. So that's going to give us, well, that's enough information to plot this point up here. That's our starting point. So I'll just write that in sort of coordinate form. That's going to be 0.2083, 0.12. Okay, so we figured out the first point on our McCabe-Thiele diagram. So let's go ahead and figure out the final stage, this point up here. So that's going to be xn and yn plus 1. So xn is going to correspond to this stream down here, right? Because it's going to be the composition of A in the final overflow stream. So xn is going to be equal to A, which is 0.5, divided by the total mass of solution, so 130 plus 0.5. So that's going to be really, really small number, 0.000338. So effectively 0. And then yn plus 1, that's going to be the concentration of A in our solvent stream. And since we're told in the question that it's a pure solvent, there's going to be no A in that stream, so hence yn plus 1 is going to be 0. So now we've got our second point. We've got 0.00383, and we've got 0. So that's point 1, that's point 2. So the next step is to figure out the coordinates of this intermediate point here. So what we're going to do is we are simply going to calculate the x value simply by taking the average of this value and this value. That's going to give us a point that's somewhere in the middle. And by doing that, we can, construct a line of best fit and see how the curve varies. So it's kind of arbitrary where we pick it, but choosing it in the middle is gonna help show sort of any curvature in the curve. So let's calculate that. So x operating, you can just about still see that. X operating is going to be equal to, it's going to be x0, this one, plus xn over 2, just simply the average of those two. That's going to be equal to 0.10605. Cool. So we've got the x coordinate, that's easy. We just need to figure out the y coordinate. then we're going to have 3 points. We can draw a curve and we can finish off. So we're pretty close. There's just one more step we need to do, and that's to figure out the y coordinate of this one. So I'll just put this to one side. Okay, so to sort of visualize what this intermediate operating stage sort of looks like, I'm just going to draw a really quick schematic of our sort of overall process. So we've got stage 1, we've got stage 2, something in the middle, we've got our intermediate, let's call that capital N, and then we've got a few more stages, and then we finally end up at our finish little n, which is what we calculated earlier. So previously we've looked at this stage, and then of course we've got streams coming in, streams coming out at each end. So instead of looking at sort of the overall mass balance, now we're sort of more focused on this stage here. So we could draw a mass balance around just this box, and then use that to figure out the concentration of the streams coming in and solve for y. Problem is we actually don't have enough information to do that, and the reason is because we don't know anything about this stream coming in, we don't know anything about these streams coming in apart from the concentration which we calculated. So in order to help us solve for all the unknowns, what's probably a better idea to do is to take a box around this whole sort of left hand side of the process, if you like. So if I draw a box here, that's going to encompass stages 1 all the way to this midpoint, so stages 1 to capital N. Yeah, try not to get confused between the capital N and the small n. This one here refers to the intermediate operating point. This refers to the final stage. I think in the notes it might be different, but for this question we'll just work with capital N for now. So if we take a box all around this, we've got our final solution coming out and our initial solid coming in. So that's going to be just exactly the same as what it was equal to earlier. So from before, we said that this was going to be equal to 9.5. B is going to be 0, and C is going to be 69.67. And likewise down here, A is equal to 10, B is equal to 52, and C is equal to 38. And then it's these streams on this side of the box that we don't really know about. So let's just draw those in, and let's label them as well. This was L0, this was V1, this is going to be Vn plus 1, and this is going to be L capital N. Just keep those capital N's consistent. So we know, or from previously we worked out that the concentration of the X stream, or the underflow stream, is going to be 0.10605. So that's going to correspond to this stream down here. We're looking for the Y composition. So that's Y is the composition in our overflow. So that's going to be the composition of this stream up here. In other words, we know about this stream, but we want to figure out what's up here. So if we do our material balance, we can figure that out without too much effort. So A, let's just make sure you can see everything. Okay, so A is going to be equal to, we don't quite know at this stage, we're not given that. We know B is going to be equal to 52, that's just the solid is retained in the underflow. And we know that because, according to the question, the ratio of dry solid to water is going to be 2.5, that's going to stay the same. So this is still going to be equal to 130. And we know that the concentration of X in this stream, or concentration of A in this stream I should say, is going to be equal to 0.10605. So using that and the rest of the information down here, we can solve for the amount of A in this stream. So let's go ahead and do that. We know that A divided by A plus 130 is going to be equal to 0.10605. So times each side by that, you get A is equal to 0.10605. A plus 130 times that. So 13.78. So just isolating the A on the one side, we get 0.894. A is equal to 13.787. So A is going to be equal to 13.787 divided by 0.894, so that's going to be 15.42. So 15.4 is going to be our answer up here. And knowing this, we can do a material balance on component A. We can figure out the amount of A up here. That's going to allow us to calculate the concentration of A up here. And that's going to give us our Y n plus 1. That's what we were looking for. So let's fill in our unknowns up here. We've got 15... Sorry, we've got A. B is going to be 0 because it's an overflow stream. And then simply by doing mass balances, we can figure out how much A and how much C is up there. So looking at A, simply in minus out. So we've got 9.5 plus 15.4 coming out, divided by minus 10 coming in. So we've got 14.9 kilograms up here. And then exact same thing for C, because we know all the streams, 69.67 plus 130 coming out, 138 coming in. So that's 161.67 kilograms. So then calculating Y n plus 1, the concentration of this stream, is as simple as going 14.9 over 14.9 plus 161.67. If you do that, it's going to give us 0.084. So now we have our, or the X and Y compositions for our intermediate operating point. So let's just write that down. We've got 0.10605 as our X coordinate, and then Y is going to be 0.084. So we've now got our 3 points. This number 3, points number 2 are here. So we've now got enough information to plot our operating line. We can draw a line of best fit, and now we can do our McCabe sort of stepping off stages. Okay, so what I've done is I've got myself some graph paper, and I've simply drawn up the X and Y axes. I haven't labelled them yet, and you'll soon see why. Because if we look at the points that we need to draw, we've got 0.2, 0.1, almost 0, almost at our origin, and then the other point was 0.1, 0.084. So these are actually all quite small numbers. So if we went from 0 to 1 on both axes, we'd end up having all our data in this one little corner, and that's going to make the stepping up stages really quite difficult. So our highest value, I think, is 0.2. So let's extend these axes out to maybe 0.3. Okay, so what I've done is I've just plotted those 3 points on the diagram. I've just labelled them here. So we can see 1, 2, 3 don't really lie in a straight line, so that's why we need to do sort of a smooth curve for those. So let me do my, my best attempt at joining those up. Probably about as good as I could have hoped for. So now we just simply do our standard McCabe-Thiele analysis using the stepping up stages. So this shouldn't be anything too difficult, apart from the fact that we've got quite a sort of an approach down there, so that might make it a little bit tricky, but in terms of the actual process, isn't too hard. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. Remember, those are ideal stages, so we're not quite done. The question asked if the overall stage efficiency is 80%. So the number of stages we actually need is going to be 12 over 0.8. So that's going to be equal to 15. 15 exactly, so no rounding issues there. Yep, so that is how you solve a variable underflow process using McCabe-Thiele. Just something I wanted to mention with regards to how we calculate these x and y values. Remember we had our operating curve equation, and when we had a constant underflow process, we said that L over V was constant, and we just simply plot that. I guess I just want to note that this operating curve equation is still absolutely valid, and it still actually describes this curve that we've drawn here, so that operating curve is still true. Because the operating curve is just based on a mass balance. So if you wanted to, you could have actually calculated all these x and y coordinates using that operating line equation. The reason I didn't do that is just because it involves fewer variables or fewer unknowns, and to me it's a little bit more intuitive just to calculate x and y at the different streams. But if you want to, and if you want to use that operating line equation to figure out x and y, there's absolutely nothing wrong with that. So that would give you the exact same answer. Like I said, the operating equation is derived from a mass balance, so it doesn't matter which way you do it, you're going to get the same answers. So that was just something I wanted to sort of clear up.